Well, welcome everyone to our weekly AITRN seminar. The speaker today is Bianca Dornelas, and the title of her talk is Collapsing Higher Order Czech to Higher Order Delaunay Complexes, Current Results and Open Questions.
Yeah, thank you for the introduction. And I will just add that this is ongoing work with Michael Kerber, but there are some special appearances from Michael and Don, because in fact, we started looking at this problem back in 2019, and then Michael was still working with us, but we didn't quite manage. And then in 2021, Michael was talking with Don about it, and then Don gave an idea, which is actually the idea that last year me and Michelle decided to dive into and try again. And that's what I'm going to talk today. And I will start giving a very brief introduction of things I assume most of you know. But if you don't know and you have any questions, just stop me. So it comes as no surprise that this is a TDA work. And especially in the area of persistent homology, right? We are looking at some data points, which I'm going to call sites, and we want to identify topological features of it. So for instance, here we would like to see this is a circle. And one way one can do this is start growing balls around the sites and looking at this region covered by the balls. And then one can see that there will be several connected components. Then the number of connected components will start decreasing. And eventually, there will be a whole one cycle present there. And along this process, we keep track of the radius and the variations. And then eventually, the balls will grow enough so that there is no more changes. And then one can see, okay, so there was one cycle that lasted for 75% of the time where there were changes. So probably this data is representing one cycle. And that's good. Then we can say, okay, this is a ring. But there is one difficulty with this union of balls approach, which is that it's very sensitive to outliers. So if we do introduce some extra sites like these red ones here, what will happen is that our one cycle is going to die much faster. So we can see that the lasting interval of this one cycle was reduced to 25% of the whole interval. And so the question arises whether we would like, is it possible to adapt this to reduce the sensitivity to noise? And one way one can go about that is to think also the way we think when we look at this image, because we could say intuitively that these sites here are probably the non-outlier ones, and these are the outlier ones. And what the process that's going behind that thought is very likely to be that the outlier points are much more sparse, and these ones are much denser. So one way we can transform the balls region into a dense region is to look at the intersections of balls instead of the balls themselves. And that's what we call the k-fold cover. So for k equal 1 is just the normal union of balls, and for k equal 2, we can see here is the regions covered by at least 2 balls. And as we can see here already, the one cycle now is going to be surviving when it would be dead on the k equal 1 case, and it dies a bit later, so about 50% more of this last interval. So this k-fold covers arise in this context of dealing with outliers. And this is the main motivation for studying them. And what we're going to look at now is how do we computationally study these k-fold covers, right, which are simplicial complexes. And there are many of them that one could look at. There are the degree ribs and the higher order Czech, Delaunay, and Delaunay Czech. But for us, the higher order Czech and Delaunay are the most important ones. So I will briefly introduce them. The higher order Czech is pretty straightforward because it's just the nerve of the k-fold cover. So what we do is, given some sites, we start growing balls around them, and then we look at the region covered by k balls, in this example 2. So here at this radius, we have no intersections, hence the Czech complex is empty. And then eventually, there will be some intersections appearing. And we call these regions here lenses. So whenever k-balls intersect, we call that region a lens. And in the nerve, that region is going to correspond to a vertex. And that's what we do. So the balls continue growing. Sometimes there are no changes. Sometimes, besides vertices, there will also appear edges. So for instance, this edge here is because this left big lens is intersecting for the first time this middle big lens in this small lens here. And also the small lens is an intersection of itself with the left lens, for instance. So we also have this edge and so on. And moreover, we also have that the small lens is an intersection of itself, the left big lens, and the middle big lens. So that corresponds to 3 vertices interacting, hence we also have triangles. And we can continue like that, just taking the nerve. So here you have an animation of the whole process. And you can see there that even though we just start with few vertices, all of the sudden there's lots of simplices going around. And that is the whole higher order check complex, in this case for order 2. Now, there is another approach, which is the higher order Delaunay complex, which is a bit cleaner than this one. And the way it achieves that is by looking into the higher order Voronoi regions. So just to recall here, the standard Delaunay complex is just the nerve of the standard Voronoi diagram, right? Where you tessellate the spaces into regions with the same closest neighbor. And here, if we are not yet thinking of a radius and not considering the k-fold cover, we just extend this definition of Voronoi. So we have now the k order Voronoi diagram. And this is just a tessellation into regions with the same k closest sites. Again, I will do an example for k equal 2. So we can see here that this region has these highlighted sites as the 2 closest ones. And then the rightmost region has these other 2 highlighted sites. And then there are these middle regions, for instance, that have also the highlight sites as the 2 closest sites. And so what we are going to do for obtaining the Delaunay of that is just taking the nerve again. And again, here I'm not talking about a radius yet. So for each Voronoi region, we are going to add a vertex. And now here it is important that if we have sites A and B, then our vertex, we are going to call it the vertex of the subset A, B. Right, so this is an abstract complex that we are building. So again, here there's another Voronoi region, another vertex, and we continue like that. Now, I told you this is an abstract construction, and yet we are seeing a geometric realization of it. And of course, there are some choices involved in that. And in fact, not always the higher order Delaunay is geometric realizable. This example is an exception. But to be consistent, here I have to tell you that I have been putting the vertices into the barycenter. So for instance, AB is in the barycenter of A and B. And then BC, also it's in the barycenter. So to keep consistent, I will shift these 2 vertices here to the barycenter. So remember, this is the vertex from A and C. So let's shift it to the barycenter there, right? We do these 2 shifts. And so obtaining the vertex is just a part of taking the nerve, right? We have to continue. And next we go to the next dimension, which are the edges. So for each Voronoi edge, we are going to add a Delaunay edge. So remember, this region here had this vertex, and this region here had this vertex. So an edge in between these 2 regions gives us an edge between those 2 vertices. And we continue like that. Don't forget that we shifted the vertex from here to the barycenter. So this next edge is here. And continuing like that, we have all the edges. And then finally, for a Voronoi vertex, we are going to have to add a triangle. So again, this region is this vertex, this region is this vertex, and this one is this vertex. So this Voronoi vertex corresponds to this triangle. And if we do that for all the Voronoi cells, we obtain the higher order Delaunay complex. But of course, we are interested in a version with radius so that we can relate this to the k-fold cover. And the way we do that is just to intersect the k-fold cover with the k-th order Voronoi diagram. So we intersect our lenses with the Voronoi. And only after we do this intersection, we take the nerve that will give rise to the k-th order Delaunay with the radius r, where r is the size of the balls of the lenses. Now, something interesting that happens here is that some simplices that would be in the Czech are not there in the Delaunay. So for instance, if we take a look at this highlighted lens here, that is the lens between A and C, right? So this is the ball around A, this is the ball around C. We can see that the corresponding Voronoi region here is not yet intersecting that lens. So that means that at this radius, even though this lens already exists as a vertex in the Czech complex, it does not yet exist in the Delaunay complex. And in fact, in this radius, the Delaunay complex is just this, 2 edges and 3 vertices. So that's the main difference between the two of them. So in both cases, we are going to grow balls around the sides, and we are going to look at the intersections of K balls, and we are going to assign to each of these intersections a vertex. However, while for the Czech complex, we just straightforward take the nerve, for the Delaunay complex, we first are going to intersect the k-fold cover with the k-th order Voronoi, and then only afterwards we take the check. And as a result, we can see here in the figure already that even though the complexes are similar, the Delaunay one is much cleaner, right? It has much less simplices. And I would like to highlight here that even though I'm commonly only saying Czech or Delaunay, I'm always meaning the higher order one. So good, we have these two complexes. And what do we want to do with them? We want to extend a result from the order 1. The order 1 is a very well-studied case. And there is this interesting result by Bauer and Edesbrunner that says that the Czech complex, now with order 1, collapses through the Delaunay complex also of order 1. And we would like to extend that result. But before we go looking into how we approach that, I have to tell you what are collapses that I didn't tell yet. But that's pretty simple. So given a simplicial complex, a collapse is just the removal of a pair of simplices from it. So for instance, we could remove this triangle edge, and that is a collapse. Now, of course, the formal definition is a bit more complex, and we have to satisfy some conditions. But what you can keep in mind is just that this is a nice removal, in the sense that its outputs is still something that is a simplicial complex and with the same homotopy type. And for helping with that intuition, I can show you an example of a bad removal. So we could, for instance, try to remove this triangle and this edge. But that is bad, because if we did that, here we would have a triangle that has no edge. And besides that, we also have a one cycle created. So this is a bad removal. This does not count as a simplicial collapse. Good. So a simplicial collapse is just a nice way of removing the simplices. And what we want to do is see if there is a way that we can do a sequence of removals from the higher order Czech to arrive at the higher order Delaunay. Now, how did we go about that? I mentioned that Don gave an idea to Mikhail once in 2021, and that this was the idea we were looking into. So I will first tell you what is the idea, what's the intuition behind it, with a figure of k equal 1. What we're going to do, so here we see just a Voronoi tessellation. And what we're going to do is let these Voronoi regions grow. So we just let them grow by giving a weight to the distance. And this is interesting for us because if we look at what is happening when we intersect the k-fold cover with the Voronoi, so here we have an image of the case k equal 2. Let's take a look at one lens in particular, right? When we expand the Voronoi region, we can see that the region of intersection naturally increases. And what happens is that there will be a point where we extended the Voronoi region enough so that the whole lens appear there. And when we are looking at the whole k-fold cover, what this means is that we are going to go from the k-fold cover intersected with the Voronoi to simply the k-fold cover. And that's pretty interesting because the Čech complex is exactly the nerve of the k-fold cover, and the Delaunay complex is the nerve of the k-fold intersect Voronoi. So if we do have a continuous transformation in the cover space, this probably induces some continuous sequence of collapses in the simplicial complexes space. Right, so this was the idea. And then we had to go about how to formalize it. So the first step was to give a name to things, right? So what we did is we called these growing Voronoi regions the t-Voronoi regions. And t is just the parameter that we give for them to grow. So I will show, for curiosity, the parameterized formula, but please don't be scared. We're not going to need this formula. So we can see here that we have a fixed order, k, and then the Voronoi region of these k sites is just the points in the space that have these k sites as the closest sites with a weight t here. So we just change the usual Voronoi formula to a power distance, basically. And once we have defined these Voronoi regions, the next step of what we did was to examine what is happening in these regions before adding any balls, to see what's happening when t varies. And the first observation that was important is what is happening in the boundaries. So one interesting thing is that to notice that every line, so every edge here in the Voronoi boundary is in fact a bisector. So this highlighted one, for instance, is the bisector in between A and C. And this one here is the bisector between B and E. And in fact, we show that every line is always a bisector, also in the higher order case, right? In any order case. And what's happening when the parameter t varies is basically that we are shifting these bisectors. So we are going to have a shifted bisector to create the bigger Voronoi region. And so we decided to name these the t bisectors. So the boundaries of the t-Voronoi regions are just shifted bisectors, and they can also be parameterized by just a power distance bisector. Great, so we identified that. Now the next thing to see is that when the Voronoi regions are growing, this means that intersections that didn't exist are going to appear. So for instance, we can see this region here and this region here. They don't intersect at this point, which is at t equals 0, but eventually they will grow enough so that they will intersect. And what this implies is that there are simplices involved in this variation of t, right? So for instance, again, in this image, we have here the first time there is an intersection between these two Voronoi regions. And this very straight line is the corresponding edge. And so that's something important that's happening when the Voronoi regions are vary. And there is yet another observation, which is that sometimes, so here we have yet a larger value of t. We can see that sometimes, look here, there will be new t bisectors appearing in the boundary. So look at this Voronoi region here. It had 1, 2, 3 bisectors on the boundary. But now, with this larger value of t, we have 4. There is one other hidden here. So this also was a very important observation to work on the proofs. Yes, then here's that written. Great. So we had all these observations on the behavior of the Voronoi regions. And the next thing to think of was, okay, how do we get collapses from this, right? We want to go to the simplicial part. So the first thing is that we saw before, when these Voronoi regions grow, there will be a point where they have grown enough so that intersecting them with the k-fold cover just outputs the k-fold cover. And this point is exactly when t is larger or equal than r. And then, of course, when t equals 0 is just the normal Voronoi regions, then the nerve is the higher order Delaunay. So if we are wanting to go from the Czech to the Delaunay, what we have to do is just let t decrease. So that means, again, that we are going to go from t equal r to 0. And while t is decreasing, the Voronoi regions are now going to shrink. And then some intersections are going to disappear, and that's going to correspond to the removal of a simplex. So for instance, again, in the same figure as before, we had that edge corresponding to this intersection here. And as soon as the regions decrease, that edge cannot exist anymore because the left Voronoi region does not intersect the right-hand Voronoi region. Good. So that means that we have some specific values of t, which we are going to call the critical values of t, when changes happen in the nerves. And of course, they have to be finite, because if they correspond to removals of simplices in the Czech complex, and the Czech complex is finite, then this is a finite number. However, there was still some difficulty here, because it could be that we had a Voronoi region, a Voronoi tessellation, sorry, where we had here the Voronoi of A and B, and then far away, we had the Voronoi regions of C and D intersecting at the same time. And then we had lots of other Voronoi cells in the middle, and they did not interact at all. So it could be that we had two completely separate groups of simplices that are disappearing at exactly the same time, but they are disjoint and they have no relation. And then we would get confused when separating the intervals to collapse. So what we would like to do is to identify these groups, each one separately and uniquely. And for that, we decided that we wanted that the first intersection of two Voronoi regions be a point. So exactly like in that image, right? So in that image, we had Voronoi regions that first intersected here in a point. And then if we have that, we can define critical pairs instead of only critical times of point and time. So that would mean that we have this point X here is a critical point. And if we had that other place somewhere far away, also with an intersection disappearing, then we would have two distinct points, even though we had the same time for both of them. And then that's great, because once we have the critical pairs, we can identify all the simplices that are associated to a single critical pair. And we can analyze the simplices, and then turns out that there is a single maximal one, and there might be several. There might be also a single, but it's possible that there are several minimal dimensional simplices in this batch. And then it becomes just a matter of combinatorics to pair up the simplices in a way so that they all can be collapsed away. So great. This defines the collapses, and that's all we need, right? However, here, there's something that we want, and we do not have yet, right? So we want the first intersection of Voronoi regions to be a point. And the next thing we have to do is look how do we get that. So let's go back to our observations of the boundaries of the Voronoi regions. Remember that they were t-bisectors, namely just shifted bisectors. And of course, a bisector is just an hyperplane. And we can, in particular, give a notation for it. So this here is a bisector in between the points A and B at the time t. And they're just hyperplanes. So when we want that the first intersection of two Voronoi cells, so again, I will draw that here, is a single point, what we're saying is that we want that the first intersection of all the bisectors in the boundary of those Voronoi cells intersect at a single point. So what we're saying is that we want that the first time some set of hyperplanes intersect, that intersection is a point. But that's, of course, a very strong condition. So we can think that we don't need all of that. What we need, actually, is only that the Voronoi cells that did not intersect at t equals 0, once they intersect, they are a single point. Because if they already intersected at t equals 0, we don't care, because those are cells corresponding to simplices that are on the Delaunay complex, and we don't want to remove them, right? So, in fact, we're only interested in hyperplanes that do not intersect at t equals 0. So I would just make a drawing here to maybe help with the intuition. Let's say we are in the space and we are looking at the space from above. And then we have 3 hyperplanes. So these are 3 hyperplanes. And then at t equals 0, this is their situation. So even though they pairwise intersect each other, they do not intersect the 3 of them. Now, if we let the time grow, we are just shifting these hyperplanes, right? So, oops, this is not a good color, sorry. So we are just shifting these hyperplanes. And we are going to get something like this. And then eventually, what will happen is that they will actually intersect, right? We are going to have an intersection here in a point. And this is exactly what we want. So we want that a set of bisectors that do not intersect at t equals 0, when they first come to intersect, they will be a single point. So we looked a bit into how to guarantee that condition. And turns out that what we actually need, so it is sufficient to say that if m t-bisectors that did not intersect at t equals 0 intersect, then the dimension is smaller than d minus m. So let's repeat the same example as before, just to understand this bunch of variables. So here we had 3 hyperplanes, right? So m equal 3. And these are 3 hyperplanes that do not intersect at t equals 0. So they are in the condition. And we want that when they intersect, their dimension is smaller than d minus m. Since we are in the space, d is 3 and m is 3, so this is 0. And in fact, when they did intersect, we saw before, what has happening is was exactly a point. So the dimension is 0, and that is good. That is such a set that we want. And so we saw, okay, this condition is sufficient. And then we gave a name for this condition. So we said that a set of sites is in a strong general position if for any collection of bisectors that do not intersect at time 0, so remember here we have the parameter of the time, and they do not intersect, then once they intersect at some time greater than 0, then their dimension is at most d minus m. And with that, we basically finalized our list of ingredients. So I will restate all of that again to give it some structure. The whole idea was we are letting these Voronoi regions vary with a parameter t. And we saw that if we let them go, we can go from intersecting them with the k-fold cover. We can go from something that gives the Delaunay complex to something that gives the Čech complex. And because of that, we want to decrease t, because we want to go from the Czech to the Delaunay. And the value to do that is exactly from r to 0. And while we are decreasing, we want to be able to identify some groups of simplices that we can remove according to the current time. So, but to ensure that we can identify uniquely these groups of simplices, we also want that the Voronoi regions that are varying, when they first intersect each other, that they intersect at a point. And for that, we need this strong general position condition. But if we do have it, then we can identify the critical pairs x and t. And then we can find these associated simplices. And it's just a matter of combinatorics of how we collapse the simplices away. In some cases, there will be only one interval. Some cases, there will be several, but it can be done. And so this all together gives us this result. So we did manage to show this theorem that if we do have a set of sites in any dimension that is in a strong general position, and then for any order, so again, k is the order, we can collapse the higher order Čech to the higher order Delaunay complex. And now comes the point where I will remind you that this is all ongoing work. And so if we do have this result, how come this is ongoing work, right? So I ask you, where is the catch? And I will give you some seconds in case anyone wants to venture, given a hypothesis of how come we are not satisfied with this theorem. So I guess no one wants to venture. I did a good job of convincing you, I can see. But I will tell you, of course, the catch is exactly in the condition of a strong general position. Because we don't know if it is generic. And in fact, this result is not that relevant if it's not in a generic condition, right? And we are in the process of trying to show this. And what we are doing now is actually something pretty elementary that involves bases and orthogonal spaces. But it's still, I have been finding in my experience that these elementary proofs are sometimes the hardest. And in fact, we haven't managed yet. And even more than that, all the counterexamples we could build, so all the spaces we found that was not in strong generic position, were in fact also not in the standard general position. So there is even the question whether maybe the standard generic position is sufficient, and we just fail to see how to use it to guarantee that these Voronoi regions always intersect first at a point. And yeah, so we are still working on that. And this is the ongoing part of the work. But of course, there are further open questions. So just for completeness, I can tell you one natural line of questions comes from the fact that the original result by Bauer and Edersbrunner for k equal 1, I forgot to write that, so k equal 1, is actually larger than what I showed before, right? So we can see here. They show that the Czech collapses to the Delaunay Czech complex, and then the Delaunay Czech collapses to the Delaunay, and then the Delaunay collapses to the rep. And of course, it's only natural if we are wanting to look at the higher order case to ask, can we also adapt this approach to work with the Delaunay Czech and with the rep complex? But then we realized, actually, if we want to work with a higher order wrap complex, we need to define that first, right? Because that's not defined yet. So is there a minimum definition of higher order wrap? And that's in some sense also ongoing. I did try some definitions. I could not prove they were well defined yet. So yes, all of these are open questions. So I will finish just giving you a summary. So the motivation for this all comes from the fact that the k-fold covers are interesting for dealing with outliers. And two ways of looking at the k-fold cover are the higher order Čech and Delaunay complexes. And the Čech is just obtained by taking the nerve of the k-fold cover, while the Delaunay, we first intersect the k-fold cover with the higher order Voronoi regions, and then we take the nerve. And then we were looking at how to collapse the Čech into the Delaunay. And for that, we got this idea of letting the Voronoi regions grow and tracing the changes according to the new intersections in the Voronoi regions. But for that, we wanted these intersections to be of a low dimension enough. And we required this strong general position assumption, but we are not sure yet that it is really a generic assumption. So with that, I conclude, and thank you for your attention, and I'm super open for questions.
Thank you. So maybe before we get to questions, I would ask everyone to unmute themselves so that we can give a round of applause for the speaker today. Okay, and now it's time for questions. Unmute yourselves and ask, or raise your hand, whatever method you prefer.
I'll start with a comment. So I just put it in the chat in case my sound is bad. But I was involved in a project where we thought some things should be generic, but we couldn't prove it. And then a very helpful reviewer taught us a lot of algebraic geometry that we ended up needing. And they were so helpful that we tried to add them as an author, but they didn't want to be added as an author, so we don't even know their name. So it's a very different context, but still, like, it was a useful technique. So maybe it's just worth looking at to see if there's any techniques in there that feel like they might be helpful.
Nice. So you did manage to prove it was generic in the end.
The reviewer did.
Yes,
yeah,
of course,
like,
yes.
we like had to resubmit it like 3 times. And the reviewer, with the reviewer's help, we finally got it. Yeah.
Nice. Yes, I will definitely take a look into that.
Other questions for Bianca? You can just feel free to unmute yourselves and ask. So Bianca, I think like in the beginning, you were talking about the outlier detection. Have you worked out in exactly what way you can use that for outliers? I mean, is sort of, or is that just was the motivation to start thinking about it?
So that's more of an empirical observation
Mm-hmm.
so far, because we have these there.
Mm-hmm.
We can observe this, that it does happen. So Zoom is in front of my screen. I'm not sure how to remove that. Well,
but you haven't sort of done like a lot of experiments to like.
No, yes, I was just telling Henry before we started the talk that I have done everything theoretical and now I'm tired of theory.
Okay.
So we didn't do many experiments, but we can see that it does help. And in fact, the main proposal is not necessarily to look at a random a random number of k that's greater than 1.
Mm-hmm.
But the main proposal would be to look at all the numbers of k, right? So that would be the multi-cover, which has 2 parameters. And then an algorithm could detect how the same one cycle, for instance, even though it's short in the k=1, it's a bit longer in the k=2, and maybe it's even longer in the k=3. And then analyzing not only the variation on the radius, but also the variation on the order, an algorithm could maybe have a more accurate output.
Okay, so we do in between question in the chat window appeared. If I understood correctly, the only examples of non-strong general position you found are examples where the points were in non-general position. So there is a possibility the general position and strong general position are equivalent.
Indeed, the examples we found were in non-general position. That is true. I'm not sure if they are equivalent is a possibility. I guess theoretically it is a possibility. I'm not inclined to claim that, though. What might be true is that general position suffices for our purposes. Like, we think now that strong general position is what we need, but it might be that general position is already enough. But even if it is enough in our purposes, that does not necessarily mean that general position imply non-general position.
Okay, thank you. So are there any further questions? Because otherwise I'm going to stop the recording and we're going to take questions offline. So next. Okay, so Bianca, thank you. I will stop the recording and all the other questions are offline.